So last time we were going through one of the homework problems, and we kind of encountered a little bit of a roadblock. So in the book, it doesn't actually go too in depth onto the difference between right and left singular vectors. I kind of wanted to talk more about that and justify like why the method I presented last time actually works. So first, let's look at the n by n case. So if we have two matrices that are similar, what's going to be true about them?
Same eigenvalues?
Yeah, and not just the same eigenvalues, they actually have the same characteristic polynomial. So we're going to get kind of like a similar thing happening here, where when we try to look at two different matrices, they won't have the exact same characteristic polynomial, but because they won't be like, if there's not square matrices, we don't have a good notion of similarity, but still going to work out kind of nicely. And it is true that for square matrices, A is similar to its transpose, but this is kind of a really hard fact to prove, and it's like not really super obvious. But you can check that they have the same eigenvalues. I think that might be a problem somewhere in the homework we went over at some point. But if you work out the algebra, you can actually check that that these two equations will have to have the same solutions because of the determinant of a matrix being equal to the determinant of the transpose as well. And then you just do it term-wise, right? Oh, someone just asked for the meeting link again, so let me send that real quick. Okay, continuing on from that, let's see. So what about, now we're going to look at A transpose versus A transpose A, right? So if we have A is m by n, what's the dimension of each of these?
M by m.
Which one is m by m and which one is n by n?
A is m by m and ATA is, sorry, the first one is m by m and then the second is n by n.
Yeah. So if this isn't square, then one of these is going to be bigger than the other. And because these are symmetric matrices, they're both going to have m and n eigenvalues respectively. But we can still say something about some of the eigenvalues. I think last time I said I mentioned you could use either of these, and then someone point out that in the case we we're trying to do, one of them had 3 eigenvalues and the other only had 2. And the thing is with singular values, you would see that what will happen is that all the eigenvalues that are like extra eigenvalues for one of them, they're actually all going to be 0. So let's say we have some eigenvalue of, what's the better way to do it? Let's say we have A transpose A has some eigenvalue lambda. What can we say about A transpose? And how might we prove this? So take a minute or two to kind of like reason why they might be the same or different and how you might go about showing that or coming up with a counterexample. For whoever just joined, so basically we're talking about the eigenvalues of A transpose A versus AA transpose. And point out that in the n by n case, A is actually similar to A transpose, so they're going to have the same characteristic polynomial. So now we're just thinking about what it might look like for the non-n by n case. Does anyone have thoughts?
And we could maybe use the fact that they're similar.
So with the n by m case, we no longer have similarity kind of coming into play, because similarity, we need everything to be invertible, right? Or not everything, we need the p and p inverse to be invertible. So if p and p aren't, or I guess in this case, we have like, we're trying to write this in terms of u and v, which are square, but the similarity only is really like well defined for square matrices in this case. This is kind of like a generalization of it, so we're not able to exactly use a similarity property, but we do get something very similar to it.
Can you use like determinant of ATA is the same as AAT?
Sure. How did you go about this?
Or like how
Or like,
Well, or like it was kind of, I don't fully understand the determinant of like the of A and A transpose are the same. That shows like how they have the same characteristic equation, but like I assume it's like something similar to that because AT and ATA have the same characteristic equation because you can like move around like A and AT.
so they don't, again, they don't exactly the same characteristic equation
Oh,
because they're
okay.
not exactly similar, but they will be very close. And when we go back to the problem we're working on Monday, you'll see how they relate. But if we have some lambda, right? That's an eigenvalue. Then we can say that A transpose A, is this the order I want to do it in? Or is it cleaner if I do it the other way? Yeah, let's start with this way. So yeah, A transpose A times some vector V is equal to lambda, right? Or lambda V. So now if we have A transpose, what we can do is plug in this vector AV. Right? And now what's going to happen is we can rewrite the parentheses and get this A transpose A times V. And that's A lambda V or lambda AV, which is the original vector we plugged in. So if V is an eigenvector of A transpose A, then AV is going to be an eigenvector of A transpose. And similarly, if we started with the other way around, where we had A transpose V equals, I'll choose a different symbol, say, well, no, actually will be the same eigenvalue. So lambda V, then we can write A transpose A transpose V. And then similarly, we get that this is lambda A transpose V.
Could you explain how you got the second line, like the first step of the second line?
First step of
Yeah, like that.
this one.
Yeah, like how that term.
So I'm doing is I'm looking for eigenvalues of A transpose, right?
Uh-huh.
So V, this is a vector living inside. So A transpose in this case is M by M. And this, your V is in Rn, but your AV is in Rm, right?
Okay.
So I'm taking this vector in Rm and plug it into our matrix that's M by M. And now I'm going to rearrange this. So now I have, once again, this A and this term here, A transpose AV, is going to be N by, or yeah, this one is N by N. So this is going to be an Rn, and we plug it into A. Was that what you were asking?
Yeah, kind of. Sorry, I'm still confused. So like you just chose to take the AV and put it into like AAT?
Yeah, like I'm looking for some vector such that ATW, like this is the matrix we're looking for the eigenvectors of, right?
Uh-huh.
So I'm trying to show this is true for some W.
Oh, okay.
So I'm choosing my W to be A times V.
Okay.
And this equation shows that like if I plug it in, it actually is a multiple of itself.
Okay, that makes sense. Thank you.
Yeah. So this only works in particular for non-zero eigenvalues, however, because if we have 0 as an eigenvalue of, say, A transpose A, then this vector now, this is actually 0, and 0 like trivial maps to 0, right? And we say that an eigenvalue is an eigenvalue if it's associated for some non-zero eigenvector, because the 0 vector always maps to a multiple of itself because it maps to itself, right? So really what this is saying is that non-zero eigenvalues of A transpose are equal. Questions about that? Okay, let's go back to the problem we're working on Monday. Let me pull it up real quick. So you're trying to find the SVD of A is equal to 3, 2, 2, 2, 3, 2, or one of those was negative 2, bottom right. And we found, let's see, I think I have this somewhere.
I just have a quick confirmation
Yeah,
question. So the eigenvectors of those eigenvalues would be the singular vectors, right?
yeah. So
And
when we
those-
rate this SVD as like U sigma V, we have the right and left singular vectors, and they're the eigenvectors of our two different matrices, right?
Right.
The one that's n by n corresponds to U, and the one that's n by n corresponds to V.
Okay.
And we'll see this like concretely when we finish this one up. So we found, I think it was N is, whoops, 2 by 3. So then A transpose was the 2 by 2 one, which we found as 7, 8, 8, 17. And we also computed this really large one as 13, 12, 2, 12, 13 minus 2, and 2, negative 2, 8. And it's perfectly fine to take the, to try and find the eigenvalues of A transpose A and go through it, but it's a little bit more computationally involved. So you guys can, why don't you guys try for A transpose, and then I'll just give you the answer for A transpose A, and we can see how they relate.
Just find the eigenvalues, right? Is that what you're asking?
Yeah,
Oh,
yeah.
okay.
And also the characteristic polynomial. Do you guys need more time? Okay, so what would you end up finding the characteristic polynomial for of this guy?
Lambda squared minus 34 lambda plus 225.
34 lambda plus 225, yeah. And this computation is much longer than I watch you guys do, but if you go through and actually take this whole determinant, you get same thing, but with an extra lambda for each term, right? So this factors as lambda minus 9, lambda minus 25, right, equals 0. And this factor is lambda times lambda minus 9, lambda minus 25 equals 0. And that kind of agrees with what we just proved a little bit earlier, that if we have these, if we have an eigenvalue of 1 and it's not 0, it's going to be an eigenvalue of the other one, right? And when we actually do SVD, we only need the non-zero eigenvectors, or eigenvalues rather, to get our singular values. And I think actually what's happening is like we need R, where R is the rank of A, and that's exactly going to be how many of these eigenvalues are non-zero. So because here A is rank 2, that means A transpose A will only have 2 non-zero eigenvalues. This extra eigenvalue that's 0, we can kind of just like ignore it for the purposes of SVD. Does that make sense? Okay, cool. So now knowing that we can use A transpose to get at least one set of singular vectors, let's find those singular vectors and find the ones associated with 9 and 25. And I think I didn't emphasize this that much last time, but the singular values now are going to be the square root of these eigenvalues that we have. So when we actually, well, we're going to use 9 and 25 to find the singular vectors. The singular values are going to be 3 and 5. So let me scroll back up while you try and find the eigenvectors for the 2x2 matrix. All right, do we get there? So it's A minus 25I look like, or not A, it's this one is A transpose minus 25I.
-8, 8, then 8, -8.
Yeah. So then null space of this guy is going to be span of the 1, 1, right?
Do you need to make it a unit vector or?
Yeah, we'll make it a unit vector in a second. I just want to find a eigenvector first. Then a transpose minus 9i is, what's that one?
They're all 8s.
Yep. And similarly, the null space is span minus 1, 1. Or you can also do 1 minus 1. I think that's usually a little easier to compute. Okay, everyone got that? So now we can find V. And actually sigma as well. So we're trying to make A equal to U sigma V transpose, where U is M by M, sigma is M by N, and V transpose N by N. So what's sigma look like?
Should be the singular values, like across the diagonal with zeros everywhere else.
Yeah. So this is 2 by 3. So diagonal entries are these two. And then we have 5 and then 3. And then for V, what do we plug in to get our column vectors? So what are the properties of U and V in this decomposition?
They're orthonormal bases.
They're orthogonal matrices, which means their columns are orthonormal basis. Yeah. So we have our basis for R2. We need to check that's orthonormal.
I have a question.
Yeah.
So like, I remember like, I think in the book, they like, to do like the smaller matrix of like AAT, which 2 by 2 instead of like 3 by 3 or something.
Yeah.
They like do the SVD for A transpose instead of A. Is this like part of both kind of? Because we like found the.
Yeah. So I mean, yeah, I guess that's a different way of looking at it. I was looking in terms of like the relationship between A transpose and A transpose A, and like examining the eigenvalues of that. That's also pretty much the same thing as computing the SVD of A transpose versus computing the SVD of A.
Okay, so in order to find the singular values of ATA, we just used AAT instead.
Yeah.
Okay.
So what's happening here is you have two sets of what are called singular vectors. The left singular vectors are the vectors that go into U, right? And U, well, but let me not say in terms of U. So these vectors go in U. U is M by M, which means these are eigenvectors from AA transpose, right? Our right singular vectors are vectors in V, which is n by n. So this means these are eigenvectors from A transpose A. If we're looking instead at the SVD of A transpose is n by n. So now the left and right singular vectors are switched. But they're going through the same eigenvectors because like AA transpose is like A transpose transpose 4. Did I say that right? Like, you know what I mean? If you replace A with A transpose, you get these two matrices again, just you're switching the roles. Does that make sense?
Yeah.
Right, so back to finding this V. We have these two basis vectors. Are they orthogonal?
Yes.
Yeah, and are they unit vectors?
No.
Yeah, so we need to get these into unit vectors. Do you know what the unit vectors for these look like?
1 over root 2, and then 1 over root
Yeah.
2.
So we have
It's
1 over
negative.
root 2, 1 over root 2, and then 1 over root 2, negative 1 over root 2. Oops, these should be square curly brackets. This should be, there we go. So then we can just plug these into V, and we still have to be consistent with the ones that correspond to which singular value. So for 5, we had 1, 1, and then for 3, we had 1, negative 1. So 1 over root 2, 1 over root 2. Wait, did I do that right? Yeah. 2, negative 1 over root 2. And then take the transpose of that, which will be itself. Cool. Now, how do you find these vectors for U? Using this fact that the vectors from U are the eigenvectors from AA transpose, and also the fact we proved earlier about the relationship between eigenvectors of A transpose A and AA transpose. Oh, I think I did mix something up. Yeah, this is A is 2 by 3, right? So that means that U is actually the one that's 2 by 2, and V is the one that's 3 by 3. So this is actually supposed to be U, right? Because these were coming from AA transpose. So AA transpose are the left singular vectors. My bad. So we're actually looking for the vectors from V, not for U. Because V is
V would be 3 by 3.
yeah.
Perfect. Thanks.
My bad. I should have caught that earlier. I was just too excited to go into the theory of it.
Then would you still do the like 1/sigma a vi thing, but like now it's v instead?
Oh
Or,
yeah,
like,
yeah.
You have to flip
So
it a little bit.
wait, explain the 1/sigma thing.
Because like the columns of u, like the columns of u are like 1/sigma a times vi, but like that's how it was like
Sigma.
originally, but like now we have like something flipped, so like
Okay, yeah. So we have our vectors in R2, and we want our vectors in R3, right? So back in this proof, we were saying that if we have the eigenvectors of A transpose A, we multiply by A to get our eigenvectors of AA transpose. And vice versa, if we have the eigenvectors of AA transpose, we multiply by A transpose to get our eigenvectors for A transpose A. So in this case, which one did we end up finding? A transpose A or A transpose A? Did I say same? A transpose or A transpose A? Which one do we currently have? So currently we have AA transpose. Are we going to multiply by A or by A transpose?
a transpose.
Yeah. So want to multiply by A transpose, right?
So like it becomes 1/sigma a transpose vi,
Yeah.
or ui, I guess.
Yeah. So we can write these as U and R2. So the eigenvectors of A transpose A are 1/sigma I times A transpose times each of our UI. So then what does A transpose look like? I don't actually have the original problem pulled up anymore to do. So 3, 2, 2, 2, 3 minus 2. Two, 2, 2, 3 minus 2. And then we're going to multiply each eigenvector. So take a minute or two to compute those and see if you know how to get the other vector in U as well, or in V as well.
So the whole like proof was that you're plugging in A transpose V into like as an eigenvector, right?
Yeah. So what we have here is for AH transpose, we found these vectors U, where this is 3U, or rather that should be 925, 9U, and then U where it's 25U. Now what we're saying is if we are trying to find the eigenvectors of A transpose A, then we're going to be able to put in this A transpose U1, rearrange, and then get A transpose times A transpose U1, which is 9U1, which is 9 times the vector we put in. So it's like what we're kind of doing is this A transpose that we multiplied U with, we're using that to get the eigenvalue. And then the A transpose on the left, then we're moving it so that's replacing that A transpose that we just used to get the eigenvalue.
Gotcha.
Yeah, sorry, it's running a little bit late, but I also ended up starting late because of the Zoom shenanigans. But yeah, I'll finish this up before 6:10, I think.
Are you on the East Coast?
Yeah.
Oh.
My bad. Did you guys find the corresponding eigenvectors yet?
I have 2.
Okay,
Really?
yeah. So let's start with those two. So which one did you plug in first?
The one for 5.
That was the one where they're both positive, right?
Yes. Yeah.
Okay.
I got the same thing actually. 1 over root 2, 1 over root 2, and then 0.
Root 2, 1 over root 2, 0. Okay. And then what about the other one?
1 over 3 root 2, negative 1 over 3 root 2, and then 4 over 3 root 2.
1 over 3 root 2?
Yeah.
And then,
negative 1 over 3 root 2.
Okay, and what's the last one?
4 over 3 root 2.
4 over 3 root 2. And this is the 3 over root 2. Sorry, over 3 root 2 is just normalizing it, right? That's coming from the singular value thing.
Yeah.
Okay. 2. Oh,
I didn't get the last one though.
Okay, yeah. So we can do that real quick. So yeah, so these are going to be 2 of our columns for V. Does anyone know how we get the last column? Or else know what we're looking for in V, right? V is orthogonal. Oh yeah, go ahead.
Oh, sorry. Would we just use Gram-Schmidt to find the third?
Yeah, so we're looking for an orthogonal basis. And we have 2 vectors already that are orthonormal. So we just need a third one, and Gram-Schmidt can do that. Instead of keeping all these fractions, you can also just use vectors that are also in that span, and because the scaling doesn't affect the dot product, right? So we have 1, 1, 0, and then 1, -1, 4 that are orthogonal. And we want a third vector orthogonal to both of these.
Don't you need to pick a third vector somewhere?
Yeah, so you can just pick any vector now in their span.
Oh, okay. Wait,
Yeah.
could you also do that? There's like something where you find like basis for null of AT.
Basis for null of AT.
Yeah.
I think there's a theorem later at the end of this chapter that justifies a similar computation. Well, what is it exactly? Do you remember?
It's like in order to find like the something that's perpendicular to this column space. It was like we did it before. Like the column space of A perp is the null of AT. So if you find so if you like transpose like these two vectors, and then like find the null space of that, you get your third vector. Like you can do that too,
also
right?
works. Yeah.
Okay.
Or this is what it was. What was the theorem?
I think column space of A perp.
Column space of A perp is null of A transpose.
Yeah.
Yeah, that also helps. Also, there's like a kind of also a quick and dirty way to do this. If you want to have XYZ, this is effectively the same as going through like Gram-Schmidt, just kind of like more directly, because we only need one thing, right? We don't have to actually go through the whole process. We can say that XYZ dot 110 is 0, or whoops, and also XYZ dot 1 negative 1 4 is 0, and just making sure we don't pick something in the span of 110 or something in the span of 1 negative 1 4 for each of these, right? So that says x plus y is 0, and that says x minus y plus 4z is 0. So one of the vectors that fits into this is, if you solve this, you can say 2, negative 2, 2, 1. And you can probably find a similar, you can probably find something using Gram-Schmidt as well. If you try that, did anyone do Gram-Schmidt and get something in the span of this or some other vector? Okay, that's fine. Then, yeah, this is orthogonal to 1, 1, 0 and 1, negative 1, 4, which means it's also orthogonal to the unit vectors of these. So then we just make this guy into a unit vector. So then this is 4 plus 4 plus 1 is 9. So we divided everything by 3. So then our V3 is negative 2/3, 2/3, 1/3. And then we have V is, let's see, when we plugged in the 1/2, that was the first one corresponding to 5, we got that with just a 0 attached to it. Then for the second eigenvector we had 1, -1, 4 over 3 root 2. And then this new one is -2/3, 2/3, 1/3. So then we take the transpose of that and we write A is 2, 1 over root 2, -1 over root 2, 1 over root 2, 5, 3, and that's the answer for this question. Questions about getting to that?
So if we had done this the other way with A transpose A,
Yeah.
would it have looked like essentially the two, like the left singular vectors would become the right singular vectors and vice versa? And then
Well, for a
sigma-
given A, it's going to always have the same left and right singular vectors, right?
okay.
What's the difference is which ones you find first. So if we did it with this matrix here, A transpose A, we would have gotten now the right singular vectors and would have multiplied by A to get the left singular vectors. And that's how they first explain how to do it in the book. And then this time we chose to get left singular vectors first and then get the right singular vectors by multiplying.
Gotcha. Okay.
Yeah.
Cool. And then I just did have one more question. I may have missed it, but the clarification that you said where we like plugged in A transpose U and then got that the projection, like the proof for 1 over sigma times AT. So the sigma is for normalization, right? That's why it's there.
Yeah, because it's if you're scaling it, it's not going to change the orthogonality or like the subspace it's in, right?
Okay.
So if it's an eigenvector, scaling it keeps it an eigenvector.
Mm-hmm.
Yeah, when I was doing this, I actually like forgot to do that, and I just normalized everything at the end, but it also works out.
Okay.
Yeah.
Gotcha.
I think that's just a nicer way to do it in one step that way.
Okay. Thank you.
Yeah. Any other questions? All right, cool. See you guys on Friday then.
Thanks.
Yeah.
Thank you.